start and stop that. Okay, so we have sort of putting this off to next week, but we could ask, what's the probability of the union of two events A and B, even if they're not, well, in the classical probability model, it would be just defined as this, which would equal the number in A plus the number in B minus the number in the intersection, right? So you'd have, to sort of pulling this out, and then it's just a rule of fractions that you can do this. So this would be, so the probability of the general union would be, where there's a possibility of an intersection, would be the probability of A plus the probability of B minus the probability of the intersection. So so a lot of the counting rules would go over to probability rules. Okay, and somewhere in there's going to be this idea of conditional probability, but maybe we want to hold off on that for a while. And you have these exercises, but let me see if I can pose some exercises for you that you can just figure out classical probability results for. Let's say that I have a sample space size of, let's say I have it 1, 2, 3, 4, 5, 6, 7, 8 items. And let's say event A equals 1, 3, 6, 7, and 8. Then what is the probability of A? If this is the sample space and this is the event A, then what's the probability of A? So see if you can figure that out. This is an exercise. And then tell me what you think. Or raise your hand when you have an answer. Okay, we have one person has an answer. Okay, 2 people have answers. Anyone else? Okay, well, you can check your answers here. So the answer is going to be the number of elements in A over the number of elements in S, which is going to, 3 people now. We have 1, 2, 3, 4, 5. So we have 5 elements outcomes in A and 8. So the probability is 5/8. You guys okay with that? Um, let's see. Yeah, I think we'll wait. This is the beginning of what we'll need to do. If you look at the chapter, I think connections between events is the beginning of conditional probability, independent and dependent events. and connections and probabilities and the principle. This is what we'll do next week. There are, and these both of these projects or probability puzzles have to do with the with conditional probability, um, because the and we'll talk about that next week is the probability puzzle and the Monty Hall puzzle. And the one thing we can do is the problem I mentioned. We have the tools to now deal with the birthday problem. Okay, so let's talk about that for a little bit. So the birthday problem or puzzle is given given n people, what is the probability that at least two have the same birthday? That was the same day of the year birthday. Okay, well, let's think about that. How could we? Well, first of all, we have to an answer would be given in terms of this seems like an event, right? Two have the same birthday. We have to have a sample space. We have n people, right? And they each have a birthday. But then how can we say what an outcome is for the birthdays for n people? Well, what we can do is to sort of make it, we can say, well, January 1st is like day one, and January 2nd is day two, and December 31st is usually day 365, right? There's 365 days in the year. Now, we can neglect leap years. In fact, this is a leap year, right? Because if I look at February here, I have 29 days, whereas usually February is only 28 days. So um, if we assume that some people would have birthdays on February 29th and they would sort of get left out of this. But we can that's sort of unusual, right? So we're going to actually just neglect leap year issues because they're actually since leap years are only like every 4 years and there's some restrictions, few times there's actually very few people that are born on February 29th. So let's just do the general case as a model of there's 365 days. So we have n slots, right? 1, 2, 3, n slots, and each one of them could have 365. If we just took it randomly, like the first person could have been born from either January 1st or December 31st. There's actually 365 different choices, possibilities for their birthday. Now, if we assume that the days of the year are all equally likely, so we assume classical probability model, which is actually not accurate, right? I mean, people are not, certain days of the year are more likely than others because people aren't born just randomly. There might be more in the spring and less in the fall and things like that. So there's actual distribution. So this is sort of just a basic probability. You could find that model and use that model to make another argument that might be more accurate in terms of probability. But let's do the classical probability version. That means that each person is equally likely to be born, of the n people are equally likely to be born on different days of the year. Now, we want to know the probability that at least two of them are born on the same day of the year. Well, that's the problem, right? Because if I have n people, then like all n of them could be born on the same day of the year, or n minus one of them. And so you're going to have a huge number of cases of many different ways. 3 of them could be born on the same day of the year, 4 or 5. So you'd have to add up all those possibilities. Okay, so it's complicated. Um, um, for event of same day counting. Okay, so and you can also look at a special case. Maybe you forgot. What if n was 2, right? Just as a warm up to sort of see if I have n as a small number. Well, if I have n as 2, right? Well, the the number of ways they can be born on the same day of the year. Well, okay, so we want to know what the sample space size is, right? And we could do that up here too. What's the sample space size? Well, I could have 365 days here, 365 here, 365 here. So the number of of outcomes that we have would be, since these are all independent, would be 365th to the nth power, right? So for 2, the sample space size equals 365 times 365, which is a big number, right? Okay, so um, there's lots of ways. Well, how many different ways could they have the same birthday? Well, we could have 1/1, January 1st, January 2nd, January 3rd, up to 365. So there's 365 ways for 2 people to have same birthday. Okay? Well, so the probability to, same day is going to be um, 365. That's how many outcomes are in the sample space over 365 times 365. So the probability is 1 over 365. So it's one chance out of 365. So that's relatively small, right? It's less than 1% of the time. The value of this formula is that it's a check. If we come up with an answer for n, like a formula, which is what we're after, so we can calculate it for different n's, we can, deal with um, this. And so the counting over here was in this project here, right? So here's where this counting, see how many ways are there for the one person to have a birthday? How many ways are there for at least 2 people to have, in a group of n people to have the same birthday? How many ways for at least 2 people in a group of n people to have different birthdays? Okay, because if we go here to P3 and we want to do the counting, well, we have 3 people. Well, the sample space size for 2, for 3 would be 365 cubed, 365 times 365 times 365. But then how many ways could 2 people have the same birthday? Well, that you can sort of see how it's beginning to be more complicated, because you can see, well, there's 3 people, and there's first the way there's the ways that 2 people have the same birthday, right? Well, it could be there's different numbers of, for example, if I have 3 people, A, B, and C, it could be that A and B could have the same birthday, A and C, and then B and C, and then A, B. This is only for only 2. Then the 3 of them could be A, B, C, right? So they could all have the same birthday. Well, so these are all, if as long as these are only 2 and these are 3, these are going to be mutually exclusive events. So I'd have to calculate the probability for all four of them and add them up. So for AB, well, this should be like 1, 1, 2, 2. There'd be 365 ways they could have the same birthday. And if I put C here and they can't have the same birthday, there's going to be 364. So each of these three, there's going to be 3 times 365 times 364, right? 1, 2, plus 365 for the one where they're all the same. So this is the probability. So then I would say this is the number of counting. So the probability for 3 people would equal 3 times 365 times 364 plus plus 365 over 365 cubed, which isn't so bad, but you can see it's like, well, what happens when I get up to like 50 people? There's going to be an impossible number of different possibilities to add up. Oh, why 364? Because if we're choosing for this one here, we're choosing these events here and saying it could be AB, AC, or BC. Well, in all those cases, 2 of them are the same and can be any 365 days. But the third one has to have a different birthday. So the reason it's 364 is because they can't be on this birthday because we're counting that separately. Because there's 300 and there's going to be, okay, so there's the pattern. So the upshot is that it is going to be better or easier to count ways that no one has same birthday. And then subtract that from the total number of ways. So we have ways at least 2 have same birthday equals total number of ways minus ways no one has the same birthday. Okay, it's a principle of exclusion and exclusion and inclusion. Okay, so we know what this number is. This number here is the size of the sample space, S n, which equals 365 to the nth power. This way we can count. We saw before this is difficult, except for n equals 2 and 3. So so we want to count the number of ways that n people cannot have the same birthday. Well, we actually know how to do that from counting. There's n slots here, right? The first person could have, say, any of 365 birthdays. The next person, well, they have to avoid whatever birthday these got, so there's going to be 364 possibilities for them. The third person, 363, right? And it's going to keep going down. You can see here, this is 365 minus 0, 365 minus 1, 365 minus 2. So this is going to be 365 minus n minus 1. Because if I put in 1 here, you got 365. I put in 2 here, n minus 1 is 1. You get 364, 363. So this is the number. This is the um, last number. So the count is the number of ways here is going to be 365 times 364 times 363 3 dot 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 365 minus n minus 1. Okay, you guys okay with this? Now, this was something we did before. It's the number of ways of choosing sequences, because we have a sequence of people, and we have n slots, and we have 365 objects to put the days of the year, possible birthdays to put in each slot, and we're saying they can't be in the same slot, because otherwise two people would have the same birthday. So we want to write this number as a factorial, so we can see this is equal to, the next number after the n is 365 minus n, right? The one that's left out, because this is n minus 1 is getting large. The one I'm subtracting is getting larger, so this is going to equal 365 factorial divided by 365 minus n factorial. Okay, so what is this is the number of ways that two people that no one has the same birthday. So the number of ways that two people might have a birthday is going to be this total number minus this one. So the number we want, number at least 2, same birthday, is going to equal 365 to the nth minus 365 factorial over 365 minus n factorial. Okay, well, that's the counting problem, and we actually want to know what's the probability that this happens. That's what you actually want to know for n people. That's going to equal 365 to the n minus 365 factorial over 365 minus n factorial divided by the sample space size, which is 365 to the n. Well, so the probability that n people at least two have same birthday is going to equal the 365 to the n, 365 to the n cancels. That's going to be 1 minus, and this will divide this. We can put it in the denominator. It's going to be 365 to the n divided by 365 minus n factorial times 365 to the n. So that's the answer as a formula. So it's obviously if we want to figure out, well, for what n is this 1/2, right? Towards 50-50. What do I, so the answer question is, using this formula, what is smallest value of n with the probability here being greater than equal to, say, 90%? Because that'd be almost certain to be, and then you could ask, well, what about 50% or something like that? Okay, well, you have to do that with a formula, right? And so the way to do that is with WX maxima, or another program like WX maxima. Okay, and this is, for example, if I was to put a problem like this on a demonstration, what I would do is I would change it up a little bit and say, what's the probability that two people, if a group of n people have a, like, what's the probability that if you have 30 people, what's the probability that they were born in the same day of the week or the same month? Or if it was like Martians, where it has like a year of 546, what would be the probability that that out of say 30 Martians that they have out of 30 Martians, what's the probability that at least two of them have the same birthday? So you'd need to be able to put another formula into WX maxima and use that to calculate the result. Now let me show you how. So I would like to do a probability here where I put in a number n and get an answer. Well, what you do in WX max is put a colon here. So you can put in, now you could do this in Python, but I think the problem here is that the real problem with Python is you don't have a factorial function like this that's as nice as the one here. So I think it'll be simpler to do it here. And let's say we just have, you can see that P of n as a function equals 2 star n, right? What did I do? Oh, yes, I think we need a function. So I think we need an equal sign here. I always forget this. Yeah, there it is. Okay. So P of n is an assignment. If I can do A5 and that gives me that. But if I want to do a function here, I have to do it like this because then P of 2 is 4, P of 3 is 6, right? So this gives you the syntax for so what we want here is P of n equals 1 minus, and it would be 365 factorial divided by, if remember the parentheses here, parentheses, then another parentheses, 365 minus n factorial times 365 up caret n, I think, close parentheses, and then this would give you the formula. And let's just check here that, see, 2 up caret 3 should be 8, and 2 up caret 4 should be 16. So that's giving you the right answer. So you can see that you'd have here 365 up caret 5 would be some big number, and then you'd be doing it as n inside this function. And so what you can do is then begin to answer questions like, in terms of probability, what probability do you how many people do you need to have a probability that's just above 50% or 90%? And that's the kind of question that you need to sort of understand this a level of understanding. Okay. So you want to study the birthday problem so that you can answer other similar questions and get the answers by using WX maxima. So you'd have to actually use some program like this to get the answers. And that's the kind of thing that we're building up to for a demonstration, and that we'll need for cryptography. I'll need you to be much more familiar with this kind of stuff in WX maxima. Okay. Which is installed in Vera Virtual. You can also install this directly, but it's a little tricky. Okay, so let's